Compensating variation refers to the additional amount of money a consumer would need to reach their initial utility after a change in the price of a good, a change in its quality, or the introduction of new products to the market. Economists use the compensating variation to find the effect of a price change on a consumer's net welfare. When there is a positive economic change, such as the fall in prices, we see the expenditure required to reach the initial utility level, U0, is less than the initial expenditure required to reach the same level of utility. So in this situation, the compensating variation could be referred to as the amount of money a consumer would be willing to pay or give up to make this positive economic change happen. Alternatively, in the case of a negative economic change, such as an increase in the prices, we can see that the expenditure required for the consumer to reach their initial level of utility is greater than it was previously. As a result, one could think about the compensating variation in this case to be the amount that a consumer would be willing to accept in order to feel indifferent about a change in prices. So let's have a look at an example, shall we? Here we have a consumer with utility function u of x and y, a budget constraint related directly to his income, and an economic environment where we have prices p of x and p of y. Initially, this rational consumer purchases good x and y in such a way that he is able to maximize his current utility at this given level of income. However, following an increase in the price of one of the goods, in this case we'll call it X, his new level of utility, which can be attained, is less than his previous utility prior to the price rise. So as is the case with most of us, the increase in price causes the consumer to substitute their consumption from good X to good Y, causing a decrease in the maximum utility they can attain and leaves them in a materially worse condition than they were prior to the price rise. So how can we empirically measure the material consequences of the rise in price on consumer welfare? As economists, we need to consider both the income and substitution effects of a price rise and not try and directly correlate the loss of purchasing power over a particular good to the change in consumer welfare. Because the purchasing decisions of individuals are both complex and interrelated, it is more feasible to use metrics such as the compensating variation to measure the overall change in consumer welfare rather than the change that can be attributed to one specific good. So again, when considering the welfare implications of a negative economic event, the compensating variation is the money or the additional income that must be paid to a consumer to make them materially indifferent to the price change. So how do we calculate a consumer's compensating variation? In all, there are three main steps that go into calculating the changes in income required to compensate a consumer for a one-off change in prices. The first step is we must optimize the consumer's level of utility subject to a budget constraint. This is done by taking the partial derivatives of a Lagrangian function and finding a point where all the partial derivatives of said function are equal to 0. We can use these demand functions for x and y to demonstrate the effects that a change in price has on a consumer's overall utility level. The problem that we face is that utility is only an ordinal concept and, as a result, does not have any tangible meaning. This is why we have to transform this changing utility into a change in income. Our next step is to calculate the consumer's cost or expenditure function. This can be done by using again the method of Lagrange to minimize the consumer's expenditure subject to a given level of utility. We can then use this cost function to calculate the expenditure required to obtain the consumer's initial level of utility prior to the price rise. So what we'll find is the difference between the new level of expenditure and the consumer's initial income is the compensating variation. So again, we have to maximize the consumer's utility subject to their budget constraint using the method of Lagrange. We then use this utility function to determine the impact of a changing price on the consumer's budget constraint, which can be seen in the diagram pivoting inwards from the blue line to the green line. If we continue to maximize the consumer's utility, the rise in the price of good X causes the demand for good X to fall as the consumer substitutes consumption from good X to good Y. We will then look to minimize cost or expenditure subject to a given utility, which we'll also calculate using the method of Lagrange. We can then use this new expenditure function to calculate the minimum expenditure required to obtain the initial level of utility at the current price levels. Graphically, this can be observed in the outward shift of the consumer's budget constraint, which is represented by the green line, to when it forms a tangent with the initial utility isoquant. The vertical translation of the budget constraint which is required to ensure that it forms a tangent with the initial utility isoquant will be the consumer's compensating variation. This should be thought of as the dollar value impact that the price change has had on the consumer's overall welfare. So let's apply these ideas to a real-world example. Toni, who lives in Perth, Western Australia, derives her utility from the consumption of two goods x and y according to the function u of x and y equals x to the power of a quarter, y to the power of a half. Initially, Toni has an income of $300 and the price of goods x and y are $2 and $4 respectively. Suddenly, the price of good x doubles. Now we're asked how much additional money must Toni receive to compensate her for this price change. So this type of constraint optimization problem is central to many of the ideas in microeconomics, and it can be solved using the method of Lagrange multipliers. The method of Lagrange multipliers is definitely a workhorse when it comes to solving optimization problems. So to start with, I'll just describe how the general form of a Lagrangian function can be expressed. So what we'll have is the Lagrangian denoted with this sort of capital L here, and it's going to be in our case in terms of the goods x, y, and the Lagrangian multiplier lambda. We also have an objective function which we are trying to optimize, as well as a constraint which has multiplied to it the Lagrangian multiplier. So our constraint is going to be g, we're going to say in this general case, of x and y, minus the constraint. So I'll just repeat that, guys. Here is what we call our objective function. So this is the function which we're looking to maximize. And here is our constraint, which is expressed in terms of the same variables as our objective function. So our first step is going to be finding Toni's initial utility prior to the price change. Initially, Toni will try and maximize the utility she derives from the consumption of the two goods. And as a result, we're going to be trying to maximize her utility subject to her income constraint. Now those two functions, both the objective function and the constraint, will fit into the Lagrangian multiplier like so. We're going to have the Lagrangian in terms of good x, good y, and the Lagrangian multiplier. We're going to have our objective function, which we are trying to maximize, which is x to the power of 1 over 4, y to the power of 1 over 2. Subtract the Lagrangian multiplier multiplied by the constraint function, which in this case is our income constraint, which is divvied out and spent on both good x and good y, and then we minus the income constraint. Now to find Toni's maximum utility from the Lagrangian, what we're going to have to do is find the first order partial derivatives with respect to x, with respect to y, and with respect to lambda, and we're going to try and find a point on the utility curve which satisfies all of those partial derivatives equals 0. So we're looking for the partial derivative of the Lagrangian with respect to x, we're looking at the partial derivative of the Lagrangian with respect to y, and we're looking at the partial derivative of the Lagrangian with respect to the Lagrangian multiplier. Now let's do the partial derivatives of all of these functions. The first one with respect to x, I'm going to take the 1/4 down the front. It's going to be 1 over 4, x to the power of negative 3 over 4, y to the half, minus lambda times the price of x. Now that has to equal 0. Now we can take the partial derivative of the Lagrangian with respect to good y. We're going to get 1 over 2 out the front. The x to the power of 1 over 4 is a constant in this case. The y now becomes negative 1 over 2, and we're going to minus the Lagrangian multiplier times the price of y. Now that has to also equal 0. Now finally, the partial derivative of the Lagrangian multiplier with respect to lambda is going to be equal to simply the constraint function, p of x, x, plus p of y, y, minus income. Now that has to also be equal to 0. Now to make this solution easier to follow in the future, let's just label this first order condition number 1. Let's label this one first order condition number 2. And let's label this one first order condition number 3. To make sure these functions are able to be manipulated in the future, what I'm going to do first is move the price and lambda to one side of the equality, and I'm going to leave all of the rest of those differential equations on the other side. I'm also going to make sure that the variables with a negative power are put to the bottom of a fraction. So the first order condition number 1 can be arranged by putting lambda price of x is equal to y to the power of 1/2 divided by 4x to the power of 3 over 4. And I'm going to do exactly the same with this function. So I have lambda p of y is equal to x to the power of 1/4 divided by 2y to the power of 1/2. Now the reason I've done this particular rearranging in the first order conditions number 1 and 2 is because I'm going to take the quotient of first order condition number 1 and first order condition number 2 as a way of eliminating lambda from our expression. I'm going to take the quotient of these two first order conditions. So I'm going to say that lambda times the price of x over lambda times the price of y is equal to this particular function here, y to the power of 1/2 over 4x to to the 3/4. Now I'm going to divide that fraction by this particular fraction here. Now, hopefully if you're doing an advanced economics course, you understand that division is just multiplication by the reciprocal. So I can then multiply this by 2y to the power of a half over x to the power of 1/4. Now this can be simplified. The 2 and the 4 will simplify to just 1/2. The y's, we can add the powers. So the index laws that go with this is going to be y to the power of 1/2 plus 1/2 over 2x to the 3/4 plus 1/4. So finally, I can cancel out the lambdas and I am just left with the price of x divided by the price of y is equal to y, because 1/2 plus 1/2 is 1. I don't need to put 1 in the power, over 2 x to the power of 3/4 plus 1/4 is x to the power of 1 as well. Great. So from here, guys, I can start to get my demand functions for good x and good y. So my first one, guys, I'm going to say that y is equal to, I'm going to take the 2x to the other side. So I'm going to be left with 2 price of x times x divided by the price of y. And similarly, for the x, I'm going to move the x by itself over to the other side. I'm then going to move the y over to the other side as well. And the x will come down. So I have price of y times y over 2 times the price of x. So we can find Toni's demand for each of these products in terms of only her income and the price of that product by substituting each of the above demand equations into our first order condition number 3. So let's start with substituting this y value in here for the y value in first order condition number 3. We're going to have delta L over delta lambda is equal to the price of x times x plus the price of y. Now instead of writing y, we write this. So 2 times the price of x times x divided by the price of y. We also subtract the income, and that has to be equal to 0. So off the bat, the price of y will cancel out, and what we're left with is the price of x times x plus 2 times the price of x times x, which is going to be equal to 3 times the price of x times x minus Toni's income has to be equal to 0. So from here, guys, we can use a little bit of algebra and rearrange it so it's x in terms of m and p. So we have x is equal to m divided by 3 p of x. Now we can do exactly the same thing, but rather than substituting this y value in here, we're going to substitute the x value in. So similarly, into first order condition number 3, we have delta L over delta lambda is equal to the price of x times x. Now rather than writing x, we have to write the price of y times y divided by 2 times the price of x. We're also going to be adding the price of y times y and all taking away Toni's income, which has to be equal to 0. The price of x will cancel with its denominator, and we're left with the price of y over y on 2 plus the price of y times y is going to be 1.5 times the price of y. So 1.5 as a fraction is 3 over 2, so it'll be 3 price of y over 2 minus m equals 0. We can then rearrange this function, so it's y in terms of income and price, and we're left with y is equal to 2 times our income divided by 3 times the price of y. So what we've found, guys, at any particular level of income and price of either good X and good Y, our demands for goods X and good Y, which maximize our utility, are going to be equal to this function here and this function here. So we've found the demand of good X and good Y, which will maximize her current utility given a particular income constraint that she has. So what we have to do now in order to find what her maximum initial utility is substitute those two demand functions back into our initial objective function, or the utility function, which I have written here. So what we're going to do is this will then be called the indirect utility function, because it measures your utility rather than directly through the amount of good X and good Y that you buy. It measures it indirectly through the prices of both goods and your income. So let's do that substitution. We'll label this indirect utility function V. Now that's going to be equal to, rather than writing X, we have to write M over 3 price of X, and all of that is to the power of 1/4 multiplied by, and instead of writing Y, we write 2m over 3 times the price of y. And all of that is the power of 1/2. So first things first, guys, I'm going to take the numbered coefficients outside of the bracket, so I can rewrite this as v is equal to, I'm going to have in the numerator 2 to the power of 1/2, and in the denominator, I'm going to have 3 to the power of 1/4, and it's going to be times 3 to the power of 1/2, so I can just add the powers, and then I'm going to multiply this new coefficient by this first bracket, m over the price of x, the power of 1/4, times m over the price of y to the power of 1/2. Great. So I can then combine my values here. So it's going to be 3/4 in the power in the denominator, and I'm going to have square root of 2 in the numerator. So my final indirect utility function will look like this. We're going to have the square root of 2 divided by 3 to the power of 3/4 times m on the price of x to the power of 1/4 multiplied by m on the price of y to the power of 1/2. So finally, to calculating Toni's initial utility. Well, we're told initially in the question that our income is $300 and the price of X and Y are $2 and $4 respectively. So the price of X is $2 and the price of Y is $4. So our maximum utility can be found by substituting these numerical values into our indirect utility function here. So we're going to have indirect utility, this is going to be maximized, is equal to the square root of 2 over 3 to the power of 3/4 multiplied by, big bracket, the income, or Toni's income, 300, over price of X, which is 2 to the power of 1/4, multiplied by 300 again, over the price of Y, which is 4, and that's all to the power of 1/2. Now, if we simplify this, guys, we can come out with a value that looks like this. We're going to have 2 to the power of 3/4 times 5√5, or approximately our Vmax, now let's just write in brackets here, this is our initial before the price rise, is going to be equal to approximately 18.803. Although utility is usually measured in utils, trying to calculate the benefit or satisfaction that a consumer derives from their consumption of, in this case, 2 goods, is abstract and difficult to pinpoint. As a result, in this problem, we're just going to observe the relative value of utility before and after the price change. Because after all, it's really the change in income required to maintain this particular level of utility that we're actually looking for. So this step is optional, guys. We've just calculated the indirect utility at the initial prices of 2 and 4. Now, we're going to observe the effect of an increase in the price of X on the consumer's indirect utility, which they derive from the consumption of both good X and good Y. So one of the benefits of algebraically deriving the indirect utility function is that now, when the price changes, we can simply input the new income and price constraints into this indirect utility function and immediately find the new level of utility which can be derived from the consumption of both good X and good Y. What we're going to do is stick our income of 300 and the two new prices of X is 4 and Y is 4 into our indirect utility function. The square root of 2 divided by 3 to the power of 3/4 multiplied by the income, which is 300, divided by the price of X, which is 4, all to the power of 1/4, times our income again, which is 300, divided by the price of Y, which is also 4, to the power of 1/2. What we could do, guys, is we could do quite a lot of arithmetic on this, but eventually it's going to simplify to 5 times the square root of 10, which is approximately 15.811. So the objective of this optional step here, guys, is just to, I guess, numerically understand that if the price of any of the goods go up, the effect of this, well, all other things being equal, is going to be that the consumer's indirect utility is going to go down. So what we're going to have to do is figure out next, how much income do I need to earn extra to compensate me for this price rise so I can keep my utility constant. So assuming Toni spends 100% of her income on the consumption of both good X and Y, we can set up the dual to Toni's utility maximization problem, which will require her to instead minimize her expenditure subject to a given utility. And just a quick side note, the expenditure function which we're going to deal with can sometimes be referred to as the consumer's cost function. So let's go about setting up the Lagrangian for Toni's cost minimization problem. So we have the price of X times the quantity of X we're going to buy, plus the price of Y times the quantity of Y we're going to buy, minus the Lagrangian multiplier times by our utility constraint, which is X to the power of 1/4, Y to the power of 1/2 minus U. Now this Lagrangian will have the following first order conditions. We're going to have the delta L with respect to X is going to be equal to the price of X, subtract lambda on 4, X to the power of negative 3/4, Y to the power of 1/2. Now this is going to have to equal 0. So our next first order condition is going to be the rate of change of the Lagrangian with respect to the good Y. And this is going to be equal to the price of Y minus the Lagrangian on 2, X to the power of 1/4, Y to the power of negative 1/2, and that's equal to 0. And finally, we have the rate of change of the Lagrangian with respect to the Lagrange multiplier, and that's equal to u minus x to the power of 1 over 4, y to the power of 1 over 2, and that's got to be equal to 0. So like we did in the first optimization problem, guys, I'm going to rearrange the first order conditions 1 and 2 so we have the price of x in terms of this particular term here and the price of y in terms of this particular term here on each side of the equality. And then I'm going to take the quotient of the prices in an attempt to eliminate the lambda term. So I'm going to take this lambda on 4 term to the other side of the equality, and I get the price of x is equal to. Now I'm also going to take this negative power of x into the denominator. So I'm going to have lambda y to the power of a half divided by 4x to the power of 3/4. Now I'm going to do the same thing with the second condition, and I'm going to have the price of y is equal to lambda x to the power of a quarter over 2y to the power of a half. Now from there, guys, I'm going to take the quotient of the prices, price of x divided by the price of y, and what we can all recognize is that division is simply multiplication by the reciprocal. So what I can do here is I'm going to write the first term down, which is lambda y to the power of 1 over 2 divided by 4x to the power of 3/4. Now rather than dividing this, I'm going to times it by the reciprocal. So rather than 2y to the power of a half being in the denominator, it's now going to be in the numerator, and we have lambda x to the power of 1/4 in the denominator. Now what our initial objective was, guys, to cancel out these lambda term, and that's what we've been able to do. And we can also combine our like terms in the numerator and the denominator. So we're going to get the 2 and the 4 simplify to 1 over 2. So there's going to be a 2 in the denominator. Now we've got the y's. We've got y to the power of a half times y to the power of a half is just going to be y to the power of 1, or just y. X to the power of 3/4 times x to the power of 1/4 is just x to the power of 1, or just x. So after all of that, we have the price of x over the price of y is equal to y over 2x. So we can go on to manipulate this particular relationship here to isolate x and y. So in the first instance, we're going to isolate y, and that's going to be equal to 2 times the price of x times the quantity of the good x divided by the price of the good y. Now we can do the same for x, where we have x is equal to the price of y times y divided by 2 times the price of x. So now we have these two equations. We're going to sub them individually into our first order condition number 3 as we start to try and develop a indirect utility function. So the first thing I'm going to do is rearrange this condition here so it's utility in terms of both x and y. Utility is equal to x to the power of 1/4, y to the power of 1 over 2. Now let's start by substituting the x value into this equation. So I'm going to have u is equal to, now rather than writing x, I'm going to write the price of y times y divided by 2 times the price of x, and this is to the power of 1 over 4, and then I have y to the power of 1 over 2. Now guys, I've created a document which I've put a link to in the comments section below, which will outline the algebraic steps required to go from utility in terms of the prices and y to y in terms of the prices and utility. So if I do all those algebraic steps, this particular function can be rearranged to be y is equal to 2 times the price of x, the utility to the power of 4 divided by the price of y, all to the power of 1/3. Great. Now let's do the same thing, but substitute in the y value. So if we substitute in the y value, we're going to have u is equal to x to the power of 1 over 4. And rather than writing y, I'm going to write 2 times the price of x over price of y, and that's to the power of 1 over 2. To finding x in terms of utility and prices, where we have x equals the price of y times the utility squared divided by 2 times the price of x, all to the power of 2/3. So what we're going to do now is substitute both x and y into Toni's income constraint, or the cost function, which is going to completely spend on both of these goods, is equal to the price of x times the number of x that we're going to buy, plus the price of y times the number of y that we're going to buy. So by substituting these in, we can get Toni's income in terms of the prices and only the utility. So let's go about doing that. We have the price of x, the price of y, u squared over 2 times the price of x, all to the power of 2/3, plus the price of y times y, which rather than writing y, I'm going to write this function here. We have 2 times the price of x, u to the power of 4 over price of y, power of 1/3. So with a little bit of algebraic manipulation, we can simplify this cost function, or Toni's income constraint, to being 3 over 2 to the power of 2/3 times the price of x, the price of y squared, and her utility to the power of 4, all to the power of 1/3. So what we've got here, guys, is the minimum cost to obtain a particular level of utility at a given set of prices, which we can use to determine how much additional income Toni will be required to earn to take her utility from where it is now to where it was prior to the initial price change. So now we have this cost function, we can find out what the income we require is to attain a given utility at a particular set of prices. And what I'm going to do first, guys, is check that this particular cost function works by essentially substituting in our initial utility level and the initial prices to see if we get Toni's initial income. So the initial utility that we had was 2 to the power of 3/4 times 5√5. And we had the price of x was equal to 2 and the price of y was equal to 4. So if I substitute these into my cost function here, Toni is going to require an income of 300, which, if you guys remember correctly, is the initial income that Toni had to purchase goods x and y. So let's find out how much income we're going to need to maintain our utility level at 2 to the 3/4 times 5√5 when the price change of x goes from 2 to 4. So now we're going to find out how much income we need to maintain our utility level at this 2 to the power of 3/4 times 5√5, but at this new increased level of prices, i.e. the price of x is 4 and the price of y is still 4. So what we're going to do is we're going to put these prices and the utility level into our cost function here, and we're going to come up with 3 over 2 to the power of 2/3 times, what do we have? We have the price of x, which is now 4, times the price of y squared, which is 4 squared, times the utility, which is 2 to the power of 3/4 times 5√5. Now that is to the power of 4, and then we've got this entire section is to the power of 1/3. Now this, if we do the simplification, we get a new cost or new level of income required to be 2 to the power of 1/3 times 300, which is approximately equal to 377.98. So after all that, we can find the value of the compensating variation by calculating the difference between the income required to obtain the initial utility at the new price level and the consumer's initial level of income prior to the price change. After subtracting Toni's income of $300 from the $377.98, the resulting compensating variation of $77.98 represents the material welfare loss that she has experienced due to the increase in prices. In finding this dollar value, we have transformed what was an ordinal measure of utility, which really only acts as a way to order or rank a consumer's purchasing preferences, to a far more tangible measure of consumer welfare.